Okay, so this uh, this this is where we left off. Okay, we're taking our history. First, Democritus came up with the idea. Then Dalton used masses to figure out that there really must be atoms, because it's the only thing that explained how the masses worked. Then Thomson found a negative piece that was in every kind of atom. And since he couldn't find positive pieces, there weren't any positive pieces for him to talk about. So but he knew the atom was neutral. So he knew he had to be some positive around, but there were negative pieces. So he said the positive is one big lump of stuff with negative pieces stuck into it. That is Thomson's model. They called it plum pudding because it was like raisin bread. We would have called it the chocolate chip cookie dough model, where the dough is like positive and the chocolate chips are negative. And that's why you get the negative pieces to fly, but not the positive pieces. Okay? So that's where we left off. We left off with so we should look at this as what we say the atom looks like. Okay? So in this model, the green stuff would be the positive stuff, and there would be a total of 5 positive charges spread out through all that green stuff. And there'd be 5 individual negative charges. And so that's our model of the atom. So Thomson did this in the late 1800s. Thomson had a student named Ernest Rutherford. Okay. His credit is given about 1910. But Rutherford, if he was Thomson's student, he probably did a lot of the measurements and built the equipment for Thomson's experiments, because the person who's in charge doesn't do all the building or running all the labs. That's what you have postdocs for. So after he graduated, Rutherford got his own lab. And Rutherford was there when the plum pudding model was invented. And it explained everything he had seen. So he said the atom is like plum pudding. Okay? He says the atom's like plum pudding. And his goal was he wanted to see how big they were. Okay? He wanted to see how big they were. So his goal was to find out how big those plum pudding atoms were. Want to measure their size. Okay? And what he used was radioactivity. We'll talk more about radioactivity soon. Next thing we're going to talk about. But there's 3 kinds of radioactivity, and he used one called alpha particles. We'll learn later more about what alpha particles are. But for us, what we need to know about them is they're positively charged and that they're heavy. They would be like the difference between the cathode ray and the atom in terms of bending by charge. Remember, we did the experiment with Thomson. When you took the atom, you had to make the charge 1,000 times bigger to make it bend. Well, the alpha particles are actually charged atoms. So it's going to take a lot of charge to get them to bend, but they will bend if you get the charge big enough. So they got some mass, and they've got a positive charge. And how you get them is you just have a piece of uranium sitting there, and it just gives off those alpha particles continuously. We'll talk more later about why it does that, but all you need to know is if you've got a piece of uranium, it's giving off radioactivity. Okay? And he knew that alpha particles could be stopped pretty easily. But if you made the material thin enough, they would go through. So he said, I want to shoot these alpha particles, these positive particles, at gold foil. And the reason why I shot them at gold foil is because gold foil is incredibly malleable. That means it can be made incredibly thin. That you can make, reading about it last night, that you could make the gold foil 10 nanometers thick and still have a solid sheet of gold foil. And the reason why I wanted to do that was he knew if he made the gold foil thick, it would stop the alpha particles. If he made it thin, they would go through. And he wanted to see where they came out when they went through. Because there's got to be some interaction between the gold and the alpha particles, otherwise they wouldn't stop if it got thick. So he wanted to see what little interaction there was with as few atoms as possible. Now, the alpha particles, you can't see alpha particles. So all you could see is, it hit just like the cathode ray. We couldn't see it when it was spinning the wheel, but we put that fluorescent paper inside. It glowed where the where the cathode rays hit. Alpha particles do the same thing. Anything charged hits that fluorescent screen, it glows. Okay. So this is a diagram of it, and you'll see lots of these diagrams today. So the lead block is here because the alpha particles won't go through lead. You put the uranium in that lead block with just one hole drilled, so even though the uranium's giving out particles in every direction, only the ones coming straight out can escape. So what he's got right here is an alpha particle gun that just shoots out alpha particles. He's going to aim at the gold foil, and he's going to see where it hits this fluorescent screen. That's how the experiment's set up. So he's looking at how those positive alpha particles are going to interact with the gold foil. And what he expected was he expected the alpha particles to pass through without changing direction very much. Because these were heavy particles, they were going to be hard to turn. Just like those atoms were much harder to turn in the Thomson simulation than the individual electrons. So expect it to go almost straight through. Just a little bit of turn, and we'll talk about why there was going to be a little bit of turn. In a second. Why? Okay, so most are going to go straight through. A few are going to turn a little bit. That's what he's expecting. And the reason why, because those positive charges are really spread out in Thomson's model. That whole green stuff is 5 positive, but it's a big region that's 5 positive, not concentrated in one little piece, like the negative. The negative's in one little piece. The positive's all spread out. And since you'd have positives spread out, it's not enough to push the alpha particles back. So the positive charges were on heavy things, so they were going to go fly pretty much straight through. He's expecting to turn just a little bit. So what he expected his beam to be about the same. Now, I drew it as a beam. Really, all he'd see is a bunch of dots. He expected just to see a bunch of dots right here. You can't see the beam. Because that positive is spread out so the positive alpha particle can go straight through it. Because he thought the mass and charge was evenly distributed, spread out all the way through. That's what Thomson's model says, is the mass, because he knew all the heavy pieces had to be with the positive, because those little light electrons didn't make up very much of the mass of the atom. Well, it's a pretty silly experiment. Why is he doing it? Okay. Okay. Well, the answer is, it's not so important that it doesn't stop, but think about when it comes out right here. When it comes out right here, there's some positive here, but there's no positive directly above it. So when it comes out of this last atom, it's going to turn just a little bit. I exaggerated how much it's going to turn. And this is going to turn just a little bit because there's no positive down here to stop it. So this positive particle is going to get pushed and turn just a little bit. And that's going to happen everywhere. So the beam is going to spread out based on where it goes through that atom. And he knew the math that if he knew how much the beam spread, he could go back and calculate how big the thing was that made it spread. Because if you make the piece smaller, these curves are tighter and it spreads out more. Just like a more curved lens spreads the light out more, the more curved the atom, the more it's going to spread out the beam of alpha particles. So he's looking to spread out alpha particles, and from how much it spread, he was going to be able to figure out how big the atom was. That was the goal of his experiment. Okay? So this is why he's setting it all up. He wants to have the alpha particles interact with just a few atoms so that they don't stop but spread out as they come out. And based on how they spread out, he's going to be able to calculate backwards how big the piece was that made them spread out. That's his plan. And here's what he got. He got what he expected for the most part. 96% went almost straight through. And there were a few that spread out. He was glad there were a few that spread out. But then he kept checking wider, and they spread out even more. And he kept checking wider, and there were a very few, just a very few, but a few that actually bounced off the gold foil. Okay? So he shot the alpha particles, expecting them to bend, and some of them bounced off and came back at him. When he saw this result, they give him this quote. When he saw those ones that had bounced off the gold foil, he said, I could not have been more surprised if someone fired a 15-inch cannon at a piece of tissue paper and the cannonball bounced off. Now, that sounds like a big exaggeration, cannonball bouncing off tissue paper. No. He did the math. According to Thomson, the alpha particle should go through that gold foil like a cannonball goes through tissue paper. That's what the math said should happen. But he had some bounce off, and nothing about Thomson's model explained why it would bounce off. So that's where I want to stop for right now. So I'm going to do something a little bit different this time. I'm going to put you in breakout rooms in the middle of class and have you work on a simulation of Rutherford's experiment, so you know where we're going. I'm going to give you about half an hour to work on that, and then we'll come back and we'll talk about that simulation and see if you saw what you needed to see. Does that make sense? So you'll see that there's Rutherford simulations there on in your module. Okay? So you're going to, there's some questions to answer. You're going to work your way through a simulation. Talk, and I put you in the breakout room so that you actually talk to each other about what you're seeing. Agree that that's what you're seeing. Okay? And if somebody says something and you don't see it, question them. Okay? Make sense? Any questions before we go? All right. So I will check in your rooms along the way, but go ahead and work that simulation, and we'll be back. It's 8:40 now, so we'll be back at 9:10, and I'll stop in along the way. Does that make sense? Okay. So I will see you in a few. So you had a small, dense, positive piece at the center. Okay, when we say mostly empty, scientists tend to understate things. This is the scale of what we mean by mostly empty. If you had a baseball field with nothing in it, nothing on the baseball field, that's an empty baseball field. But if you put a softball at second base, now that field is mostly empty. And that's not an exaggeration, that's the scale. Okay? That if the atom were the size of a baseball stadium, the nucleus would be about the size of a softball or a bowling ball. Right there in the center of that baseball field. And what Rutherford was doing by shooting those alpha particles at it is they were random. He couldn't aim them well. He could just make sure they were going straight. So it would be the equivalent of, you got a baseball field with a bowling ball in the center. You get up at a helicopter and you fly 1,000 feet over the baseball field and you start throwing out baseballs. What are the chances that you're going to hit that baseball if they're just randomly being tossed out of a helicopter? How often are you going to hit the bowling ball in the middle of the baseball field? You're not going to hit it very often. And that's how often the alpha particles bounced off. They were really rare. It's in 5 or 6 out of every million bounced off. It's a tiny number. So that told him that the nucleus had to be tiny. But because it had all the mass of the atom, because the electrons didn't weigh anything, so all the mass had to be in that tiny little place. So I've got a big mass and a small volume. I've got a huge density. Okay? So that it had to be a huge density to make it bounce off those pieces. So what Rutherford discovered was the nucleus. A small, dense, positive piece at the center we call the nucleus. And the alpha particles get deflected if they get close enough. Chemistry, disc 1. Cosmic chemistry. Side 1, 7, okay. Hey, I had some success. So, this is the actual equipment. Okay? So here's what the equipment looked like. It all happened inside here. Here's the little place where they can look in. Everything happened inside of this container. This hose, okay, the hose here is hooked all the way, and this is all about a vacuum pump because they don't want air. Air's atoms, right? So you don't want to hit any atoms of air, so they take a vacuum pump and suck all the air out of here too. Okay. So this is the uranium block. They've drawn in the hole because you can't see the hole in a piece of lead. The lead block with the uranium right in there. And instead of that big screen that went all the way around, what they actually had was a little tiny screen. Little tiny screen that the whole top spun. You could spin the whole top. And they're going to put the gold foil right here. So, alpha particles, gold foil, detector. Now they're drawing in those alpha particles. And this is what people actually saw right here. So they looked in here and they saw flashes. Okay? Those flashes, every flash was an alpha particle hitting the screen. So when they put the gold foil in there, they saw those flashes and they counted them. So they would let it run for so many minutes and they'd count how many flashes they saw. And then they would turn it 5 degrees. These went a lot further than 5 degrees. There's fewer flashes when you turn it over there, but there's still flashes. And when you hit it back, about, like I say, about 5 or 6 out of every million bounced off, so came behind here. So very few were back here, but there was enough to let you know what was happening. Hopefully that's what you saw with the simulation. And the simulation was actually used in calculating the forces on those particles. When it got close, it got pushed backward. If it went nowhere near, okay. Now I drew the nucleus right here. Okay. But if I'd actually drawn it to scale, to the size, you wouldn't be able to see it. Now think about it. If this was the picture of a baseball field, that orange place was the size of a baseball field, would you be able to notice a softball at second base in a picture like that? That's how big the nucleus is in an atom. It's incredibly tiny. So when a scientist says it's mostly empty, that's what they mean. That means, and just think about this for a second, everything's made up of atoms. Atoms are mostly nothing. You are mostly nothing. You're mostly empty. Okay. Since most of the particles went through, it was mostly empty. Why'd they go through? They didn't hit anything. And since the positive pieces turn so much, because the alpha particles turn so much, those positive pieces had to be heavy. Because they were coming in with a lot of energy. So if you've got a small volume and a big mass, you have a big density. And by big, when they say this density is large, they are understating it. If you had a teaspoon of nucleus, if you could get a teaspoon of nucleus to stay together, a teaspoon of nucleus would weigh 20 million tons. 1 teaspoon, 20 million tons. That's what they mean by it's dense. And Rutherford didn't like that answer, but that's what the math said. That the only way that you can explain those pieces bouncing off was if the piece had that kind of density. And that's why he could say, I wouldn't have been more surprised if I'd fired a 15-inch cannon at a piece of tissue paper and it bounced off. So the nucleus is incredibly dense. And of course, that's our nucleus. Now, the book doesn't go into detail how they separated between neutrons and protons. We're going to skip that part. Okay? We just don't have enough time. Got to focus on the big ideas. So now we know that there are electrons and that there's a nucleus, and we have to put them together to make an atom. So where is the electron? It can't be in the nucleus. So if it's not in the nucleus, it's got to be in all the places that aren't nucleus in that atom. Okay? Oops, sorry. It's going out of order on me. It won't let me do what I'm supposed to do. I've lost some buttons on my PowerPoint. Okay. So they did find the protons. The protons have a positive 1 charge. And I put 1840. I've actually seen people put 1837. I've seen people put 2000 because that's the idea. It's about 2,000 times heavier. To give you a sense of scale. Give you one sense of scale. If a car weighed what a proton did, an electron would be the weight of a water bottle in the front seat. Okay, because a water bottle is about 2.5 pounds. Cars in the 5,000 pound range. So that's how much smaller an electron is than a proton. 2,000 to 1. A water bottle to a car. The neutron has no charge but the same mass. They call it neutron because it's neutral. So, this is what we think of the atom. The atom is mostly empty space with 2 definite regions. The nucleus in the middle that has the protons and the neutrons, and I've drawn it way too big, but I wanted you to be able to see it. If I drew it to scale, you wouldn't see it. And the area outside the nucleus is called the electron cloud. Now, it's not a cloud of electrons. It's a cloud of probability. It's where you have a chance of finding the electron. How do I know it's not a cloud of electrons? Well, hydrogen only has one electron, but it has an electron cloud. So an electron cloud is where you're going to find the one electron for hydrogen. Oxygen has 8 electrons. Its electron cloud is where you're going to find the 8 electrons for oxygen. So to compare and contrast them and to talk about how we're not going to have to write out their names every time, the symbol for an electron is a lowercase e with a negative charge as a superscript. Because electrons are negative. So what do you think the symbol is for a proton? Go with the obvious. A P, lowercase, with a plus sign. And what about a neutron? Well, it's obvious that it's going to be an N, and it is. But how are you going to say it has no charge? You could just leave it blank, but then it would just look like the letter N. So instead, they actually write the 0. So those superscripts are their charges. An electron, when we say negative, we mean a -1. The charge comes in particles. Just like atoms come in particles, charge comes in particles. This is the unit of charge. So when we say a proton's positive, we mean it's exactly a positive one. So that a proton with its positive one and an electron with its negative one cancel each other out, and you end up with something neutral. Relative mass, that means compared to each other. If the proton weighed 1, the electron would weigh 1/1840th or 1/2000th of what that proton weighed. And the neutron would weigh exactly the same as the proton. So those numbers are pretty easy to see and compare versus the actual masses, because here's the actual mass. We actually calculated this one yesterday, figured out Thomson's, using Thomson's ratio and Millikan's experiment, we calculated the actual mass of an electron, 10 to the minus 28th grams. And a proton and a neutron, now, they both say 1.67 times 10 to the minus 24th grams. You see that the exponent has changed by 4. That's 10,000. Okay? But I hate to mislead you. So they're doing a little bit of a trick here when they give you these two, because if you go to the next sig fig, these two are slightly different. There's a little difference between the two. We don't notice it very often, but there is a little difference between the weight of a neutron and the weight of a proton. So here's the property. These are the subatomic particles we're going to worry about. Okay? What they are, where they're located. These two in the nucleus, that one in the electron cloud. And that's where I want to stop for today, so you'll have a chance to finish that simulation. I've given you a few questions about the experiments as homework for tomorrow, and I need you to read 3.3 before I see you again on Tuesday. On Tuesday, there's going to be a quiz on what we've done so far with what we know about the atom, because we're going to transition from talking about what we know about the atom to counting and measuring it, which means the math part of it. Okay? So that's the plan. So we're looking at a quiz on Tuesday. Okay? But to give you time to finish that simulation and to start that homework, I'm going to send you off in a minute, but I'm going to send you off after I tell you my favorite joke. Okay? My favorite joke. Okay. So, 3 subatomic particles walked into a bar. The proton says, I'll have a root beer. The bartender says, are you sure? The proton says, I'm positive. The neutron says, I'll have a root beer too. Bartender says to him, for you, no charge. The electron goes, hey, I've been coming for years. You have never given me a free root beer. Bartender says, hey, quit being so negative. Everyone knows you're a lightweight. And that's my favorite chemistry joke. Okay, so I'm going to leave, and it tells you all the important pieces. Positive, neutral, negative, and the electron's a lightweight. Okay, so for the rest of the period, that's what I expect you to do. Look at the homework questions out of the book, finish the simulation, get those done over the next couple of days, and get 3.3 read so that we're ready to go on Tuesday. Make sense? Anything I can clear up? Anything? Okay, so I won't get to see you, but have a great weekend. So have a good one, and I will see you on Tuesday.
Have a good weekend, Mr. Green.
Have a good one. Oh my goodness, oh my goodness, oh my goodness.